Force, work, and energy review 5. For each block, determine the acceleration down the plane in terms of g. All right, whenever we want to find accelerations, we probably want to draw a free body diagram. So there's our object, and we know we have mg acting downward. Looks like we have no friction here, so the only other force is going to be the normal force, which is at right angles to the surface. There's Fn right there. All right, well, let's see. What's going to be the acceleration? If we sum the forces, should we put a coordinate system here? Call that y, call that x. If we sum the forces in the y direction, we're going to get normal force minus, let's see, what's this? That's theta. That's going to be mg cosine theta, isn't it? Mg cosine theta. And in the y direction, there is no acceleration. So the normal force equals mg cosine theta. Perhaps we don't need that for this problem, but in most problems we will. So it's not a bad idea to find it. Let's sum the forces in the x direction. Since there's no friction, the only x component is mg sine theta. And that needs to equal the mass of this object times the acceleration down the plane, which is not 0. The m cancels. The sine of theta is 2/5. According to this picture, that's theta. So the sine of theta would be 2/5. So I think the acceleration would be 2/5 g. All right, well, let's try this one. Now we do have some friction. Usually it's given to us as a decimal, isn't it? But this time it's given to us as a fraction. So perhaps that will come into play. We always start by drawing a free body diagram. So let's do that. mg down there like that. The normal force, if you can tell by the physics of the situation, this normal force is not going to be very big. Just draw them kind of small. Doesn't matter if you realize that or not. That's fine. And then there's friction, which is going to be opposing the motion like that. And what's friction? Friction is equal to mu sub k times the normal force always. Shall I put a coordinate axis here? Call that the y direction, and then that the positive x direction. Doesn't really matter what you call them. Let's see what we can get here. Let's sum the forces in the y direction. So how about Fn minus mg cosine theta? And in the y direction, there is no acceleration. So that's 0. All right, so Fn equals mg cosine theta. And we're not given theta, but there's theta right there. And so what would the cosine of theta be? Wouldn't it be 5/13? 5/13 mg. mg cosine theta would be mg times 5/13. I think that would be what we want for the normal force. Now that is going to come into play now, isn't it? It didn't in the first problem, but it is going to come into play here because we have friction, where we need to multiply the normal force times the coefficient of friction. Let's sum the forces in the x direction. Down the plane is positive, so I think we're going to go mg sine theta minus mu sub k times the normal force. All right, so let me substitute in the normal force expression, 5/13 mg, and that needs to equal the mass of the object times its acceleration here. All right, what does that give us then? The m's cancel, so I can ignore those, and we now have acceleration by itself on this side. And you might think, oh, okay, we're done. Well, we can't leave this sine theta in because remember, theta wasn't actually given. It was these side lengths that were given. So let's change sine theta to its value, which I think is going to be 12/13. So that's 12/13 g. And then mu sub k is 2/5. 2/5. And if you take 2/5 times 5/13, the 5's cancel. So that's negative 2/13, and that's positive 12/13. So you check me on this, but I think that the acceleration is going to be 10/13 of g.